In this video, my goal is to discuss ongoing research in the Vader Lab at the intersection of visualization, artificial intelligence, and decision making. So currently, artificial intelligence is being employed in a variety of decision-making processes. When we log into Netflix, some algorithm will recommend us other shows we might like or other products we might like on Amazon. And if those decisions are wrong, if we're recommended something we may not like, it's relatively inconsequential. However, if we have artificial intelligence making decisions on whether or not your CT scan is showing signs of a particular disease, or whether or not the car should stop for a pedestrian, or whether your loan application is approved, those can have dire consequences. And in terms of decision making, um, the visualization community has had a long history of trying to think about how we can support users in reasoning about data. And visual analytics has been coined as the science of analytic reasoning supported by interactive user interfaces with artificial intelligence algorithms combined with these interactive visuals. So we have some sort of model looking at the data and feedback between the visualizations to help users gain insight and knowledge and build hypotheses about these sorts of things. So we have this natural intersection of visualization, artificial intelligence, and decision making coupled in this sort of visual analytics framework. And our lab has a history of creating all sorts of different decision support systems that are taking into account some sort of underlying intelligence to help process data and to help show this to the end users. So for example, previous work we built visual analytics law enforcement technology for helping look at crime statistics and even do forecasting for potential crime hotspots. We looked at Coast Guard search and rescue data for looking at optimizing station closures and the impacts of station closures over boating response time. And all of these take a human into the loop to try to look at different facets of the decision making process to help them understand, hypothesize, and make sense about what different decisions might occur. More recently, we've been expanding this to try to incorporate even more intelligence on the back end to try to help with the planning and resource and allocation process. One of our more recent works has been on visual analytics for oil spill response and recovery, where we take a bathymetry and ambient blowout parameter model called Blossom, and this is used to help model oil spills, particularly, let's say, a pipe burst in the Gulf of Mexico. If we know the ocean currents, the temperature, the wind, all those sorts of things, we can start modeling where the oil particles might emerge from under the water, where they might beach. And we can then start doing a visual comparison about different cleanup procedures. If we know where all the boat ramps are and what all of our resources are for cleaning this, we can now combine this with some sort of optimization and planning intelligence component to try to look at what the impact of these different plans will be. And our recent paper, published in IEEE Computer Graphics and Applications, focused on how we could develop visualization support tools for informing coastal community planning. So here we use the Blossom model to visualize oil particles that have surfaced, looking at sort of the distribution, and then we can sort of think about how much does it cost to deploy a boat, what is the distance from the boat ramp, how much cleanup can we afford, and we can compare these different profiles of cleanup spending to try to get an idea of what sort of impact will be if we can only spend X number of dollars, what will the impact on coastal communities, businesses, etc. be. Now, all of this sort of goes into the underlying concepts of our Center for Accelerating Operational Efficiency. Currently, I serve as the director for what's referred to as the CAOE. It's one of 10 Department of Homeland Security Centers of Excellence around the country. Our focus is on operations research and systems analysis, economic analysis, homeland security risk science, and data analytics. So we sit at this sort of intersection of data science, trying to think about how we can improve operations for the homeland security enterprise. And one really exciting project we have at this intersection of human and artificial intelligence decision making is where we're looking at technology that relies on a set of algorithms and techniques to solve problems that humans perform intuitively. In the Homeland Security enterprise, this could be facial identification, biometrics, more commonly intelligent illicit object detection. What I mean by this is when you scan your baggage through a CT scanner, the CT scanner is going to use some AI to identify whether there is a illicit object in there. Perhaps there's a knife, some contraband, whatever. And now the transportation security officer needs to take action once the AI alerts them to these issues. And this can be the case for things like facial recognition too. So if the goal of an officer is to use some of this artificial intelligence technology, we want to make sure that the human AI team performance is good. We want to get good throughput of travelers being screened. We want to make sure we have a very low error rate, but we also want to make sure the humans have a high job satisfaction, that they trust the AI, but that also the human has some perceived accountability for outcomes. And so working with PIs Mickey Manzanito and Aaron Chu on trying to understand these effects of human AI team performance. And this has led to more questions on human AI teaming and decision making. You know, you'd think after years of using Google Maps that we'd trust that it still knows what it's doing. But how many times do we sit in the car and we think, oh, you know, it's rush hour. I'm not going to go the way it says. I know that taking the back roads will be faster. And we're often wrong. But what's strange is that people are less trusting of algorithms if they've seen them fail, even if they fail a little bit. And they're way harder on algorithms in this way than they are on other people. So once we start showing people what happens, where the errors are, they lose trust. And an underlying goal of a lot of visualization methods in this sort of intersection of AI and decision making is to point out potential algorithmic errors for the end user to update and correct. So there are potentially concerns that visualization could contribute to this idea of algorithmic aversion during forecasting tasks, leading to reduced performance. And a lot of the things that we're trying to do are really this idea of forecasting. And so we wanted to think a little bit in our team about how are humans going to use predictions. So we have some artificial intelligence that has modeled some outcome. It creates some forecast, and we want to understand how will people make a decision with this. And so we played with this for a very toy problem using box office prediction. So when a movie comes to the theaters, it's opening weekend, it makes some amount of money, and we were trying to have humans forecast how much that money would be. So we did a user study where we built a visualization system, competed in a vast grand challenge. We won the outstanding comprehensive submission, indicating our tool was pretty reasonable. We tried looking at teamwork here, and now we're looking at sort of human-in-the-loop prediction accuracy. And so basically our subjects here get an overview of the data. They can investigate the data in the model, explore similar movies, look at the model accuracy errors and those sorts of things, and give some sort of final prediction. We had 20 participants over 9 movies. We had 3 different models of varying levels of accuracy, and we gave the users training. So we had slides that conveyed the purpose of our study. They did a practice prediction, then real predictions on movies, and then we measured their workload in this setting. And what we found is that it didn't seem to make a big difference to have allowed people to have explored these models. They didn't improve the forecasts. 72 of our subjects had a lower, 72 of our forecasts from our subjects had a lower error than the model, but 108 had a higher error. And over 50% of the predictions from our participants are larger than the model prediction errors across all 3 models. So we were trying to think about, well, if the model is quite good, if it has a high accuracy, do humans make it worse? If the model is average, can humans make it better? So while this is sort of still ongoing research and we're thinking about the design factors for this study, I think this is a really interesting area to consider about how humans are going to use these different sorts of models. And this leads us to a lot of considerations for human-machine intelligence. We might want to think about how we can do domain knowledge integration. There's domains where human background knowledge is essential and where a lot of tacit knowledge, which is often difficult to represent in an algorithm, plays a key role. Especially if we think about really complex policy decisions where we need to think about trade-offs between tax dollars, funding, political capital, and all these sorts of things. Then there's been concerns about trust. We have a lot of talk in the visualization community that visualizing things can improve trust. Studies report that forecasters may desire to adjust algorithmic outputs to gain a sense of ownership of the forecast because they lack trust in statistical models. So can these sort of human-computer interaction components help build trust? How can visualization fit in there? And likewise, how can visualization help improve learning? Typically, these types of forecasting systems allow the user to have some sort of interaction, but they allow them to change a model maybe, whether directly or indirectly. This has been very popular in the visualization community. And getting that engagement and changing the model might really change the landscape of people participating in these tasks with this human-machine teaming. But it may change the idea of accuracy in the model and how we test this, because it's going to evolve based on sort of the human input. And so we're really concerned about how we measure this knowledge integration. What's the baseline when we're supporting these human-machine tasks? And all of this sort of leads into this idea of what's really the role of visualization in AI and in decision making. And so, drilling down a little bit, right now computation analyses from artificial intelligence are often seen as black boxes. We take some data, we run some algorithm, and we create this model with a set of parameters that are going to run to completion without interruption, and they're going to make some sort of prediction. It may be a classification example. So let's say, should I classify this email as spam or not spam? Right now when you get an email to your email account, you have some sort of filter that's doing that. And while this doesn't necessarily have a human in the loop for the decision-making process, you are allowed to go to a spam folder and sort of see where things misclassified. And so with all of this and trying to understand what's going on with these algorithms to perhaps provide more insight and more trust, we've had calls for research on designing analysis modules that can repair computations when data changes and provide feedback during computation, really thinking about how we can steer this by user interaction. And this has been extremely hot topic in the visualization community for people thinking about how we can open up the black box. What are strategies for increasing user involvement? We've done this for neural networks, classifiers, decision trees, all sorts of different tools. And all of this leads to this idea of explainable AI, where we have a suite of machine learning techniques, and now we want to know what's going on in that black box. We want explainable models with high-level performance. We want to be able to say why a model made a decision. We need humans to understand, develop trust, and manage this work with the AI partners. We want to know why a model did something and why it didn't do something else. We want to know when it might succeed, when it might fail, and how to correct those errors. And you can see we've got this sort of XAI pipeline of the training data, the new machine learning process, and then this explainable model and explanation interface. And this idea of an explanation interface resonates really well with the visualization community. In visual analytics, we can combine this automated analysis with interactive visualizations to enhance understanding, reasoning, and decision making. So creating some sort of analysis loop of these interpretation algorithms and trying to understand this machine learning process to give us knowledge about the inner workings of these black boxes. And so in our lab, we've been focusing a lot on classification, where the typical machine learning class of classification is you're going to find a model for class attributes as a function of other values. So again, let's go back to our example of emails. So you have a whole bunch of emails, and we can even have labels for these as spam or not spam. And these emails have different properties, maybe length of the sentences, words being used, all sorts of different text processes that can give us features. And our goal is, if a new email comes in, our model should classify this as spam or not spam. And there's all sorts of other examples besides categorizing emails. You could say, I want to identify tumor cells, so we extract features from an MRI scan, or I want to catalog galaxies based on features extracted from telescope images. And so basically you have some sort of data set, and you want a classifier that can create some sort of split between these classes, so you can predict if it's in this sort of region for the split, it's going to be a blue class, here it's going to be green, here it's going to be orange, and of course some things are going to be misclassified, so you can see an orange dot in the green chunk and a green dot in the blue chunk. Those would be misclassifications from our classifier. Now in our lab, what we've been doing is we want to think about, well, how can we help people explore problems in these sort of classifiers? And we've been thinking about how we can visualize class separations. And in these examples of spam or MRI or galaxy data, you have high dimensional labeled data. And then we want to apply some sort of machine learning algorithm for classification and clustering. But then the challenge is, how do we help explain what occurred? What are these decision boundaries? And how do we make sense of why a particular element was classified as it was? And one of the most common ways that people in the visualization community have been doing this is by applying dimension reduction techniques. This is widely used for visualizing high-dimensional labeled data, but there's a lot of challenges in these dimensional reduction algorithms. First off, these algorithms can be linear or nonlinear, and the classification methods used can be supervised and unsupervised. So in linear dimensional reduction methods, the margins for the classification boundary can be easily understood, can be easily illustrated. You have sort of a straight cut, and it's easy to sort of explain that. That's a popular sort of thing underlying LIME, but it's unable to handle nonlinear structures. Now, the nonlinear dimensional reduction methods handle these nonlinear separations, but they can cause heavy distortions in the high-dimensional feature space, shifting things around, and can be difficult to explain those separation structures. With supervised learning methods, we optimize with in-class distributions, but then there's distortions on between-class distances. With unsupervised, there's less requirements for the data sets, we don't need labels, but then it's difficult to depict class separation and patterns. So our group has been thinking about how we can improve on some of these techniques for visualizing class separations. And our contributions have been a novel approach for detecting locally linear separations in high-dimensional labeled data sets where we have complex class boundary structures. And we developed a visual analytics framework to explore and diagnose these class boundaries. This is a way between locally linear separators and nonlinear classifiers, where we're taking advantage of easy-to-understand linear projections, but also trying to handle complex nonlinear class separations. So we're trying to find a local approximation of these complex boundaries to these sort of local linear separations. And our motivation is the decision boundaries of classifiers are often used to describe class separations. This has been popular in machine learning for local linearity analysis and machine learning, so for the LIME explainability method. And we want a set of linear approximations extracted from the original decision boundary. So if we have some sort of nonlinear classifier, we want to find these locally linear separators to help us sort of look at what might be occurring in these decision boundaries. And we want to think about how we can even create other sorts of visual abstractions to help us explore these locally linear segments. And so first, we focus on just how do we extract these locally linear segments. So we have our original labeled high-dimensional data set. Here we're just looking at 3 labels, blue, orange, green. We apply maybe a support vector machine as our classifier. And what we find is that a couple things are wrongly classified by the support vectors. And now these dots that become diamonds, those are the samples that are very near a decision boundary. We use those as seeds for trying to generate locally linear segments. So for each seed, we grab its k nearest neighbors, and we train a linear SVM on the neighbors in that location. And then we find separating hyperplanes based on the seeds. Now, as we expand this, we merge similar segments together. So for a seed in its separating hyperplane, we find the jth nearest seed among the top t nearest seeds of the same class. We merge the two, train a new linear SVM on the merged set, and we keep going. And we replace the previous 2 seeds with the new merged one to give us a simplified locally linear segment. And this allows us to then assign new data instances to their nearest segment. And so by assigning these data instances to their nearest segment, these now sort of blue blobs, we can sort of abstract those into just a group by itself. So we can say this blob is near this sort of linear segment. And this allows us to do some more visual abstractions where we can provide some macroscopic analysis as well as some microscopic analysis. At the macroscopic level, we want to show the number of segments that are being computed for this locally linear split. We want to look at the convergence of data instances under each segment and depict the locations of the segments and the relationships between these segments. And at the microscopic analysis, we want to look at the data distribution and separations of these segments, show primary features for those local segments, and explore neighboring segments and trace a path between the segments and the decision boundaries. So this provides an overview as well as a detailed analysis of specific segments. And so what we've done is we've created a segment graph. So if you think about those blobs that I showed earlier, we're going to take those and put them as a node. And now we know the relationship between those nodes and their near components. So we can visualize the segment relationships as a graph structure. where we now create a segment glyph. So each circle in our graph structure represents the size of the coverage, so the size of our sort of blob. And then we have a separation accuracy on the outer ring of all the covered data. So the ratio of the data instances in different classes are shown here, and the number of seeds is related to the size of the glyph, and then the color is the class label. Now, the edges in our graph, so we see our graph example here on the left, is the curvature, so the cosine of the angles between the separating hyperplane, and the thickness and the length is the distance between segments. So we can see how far away segment A is from segment B, see this sort of connection, look at the size of coverage, and look at the separation accuracy for the different data. We can also link these to a segment detailed view, where we use a parallel coordinate plot to show the data distribution and the number of covered instances and the dominating features for separating the local regions. And we don't just have to rely on showing this abstracted graph view. We can also just use a projection view where we're using a linear principal component analysis, or a t-SNE projection where we can allow people to toggle back and forth between the two to get an impression of the data distributions. And this linked interaction, if we highlight a segment, we can show the elements that are part of this particular graph element, this part of that abstraction. So here we have the original view. We click on one of our elements in the graph abstraction, and we can see sort of the local regions in that space. And so our goal is really to then think about how these decision boundaries are connected and present how two segments are connected with each other, and allow flexible traversal between segments. So here we've got our extracted linear segments. We know the shared seeds between 1 and 2, so we can do some sort of scatter plot series analysis, find the shortest path, and build a KNN graph on all the seed instances. And this allows for an interactive touring of this decision boundary path. And so we can interpolate bridging segments and create this interesting interactive touring interaction. So our path exploration view presents how two segments are connected with each other and allows flexible traversal between these different segments. So we can select the path in the graph, and it creates a representative scatter plot of all the different segments, showing how the path boundary traverses between these. And we link the scatter plot in this sort of zigzag way, and this interaction allows for touring between the interactive representative scatter plots. So here's sort of how our framework is laid out. And I'll walk us through a case study example of the NASA Shuttle SatLog dataset. This had 9 numerical sensor readings for deciding radiator positions, 3 classes, we'll call it RadFlow, high, and bypass. We use blue, orange, and green. And for computational purposes for demonstration, we just subsampled this into 400 instances for each class. So we have an equal number of blue, orange, and green class structures. And so here we have our graph overview of our data. After the data set's loaded, we find that 3 classes are nearly separated in the initial PCA projection result. However, the boundary between the blue and the orange class is not linear. And then if we toggle to our t-SNE projection result, we can see that the green class is clearly split from the other 2 classes in this sort of nonlinear projection. And then if we look at our segment relation view, we can see that there's 2 communities of structures, really. And the green instances are mainly in what we'd call community A, while the orange and blue instances lie mainly in community B. That's not to say there isn't some subsection of green in what we called community B, but this gives us an idea of sort of where these locally linear boundaries might be lying. And we can also go explore this outlying green segment in community B, where it contains a group of outliers from the large green cluster, and we can then look at the detailed features in the lower left view. And we can further investigate how classes are separated and the decisive features that influence the separations in local regions. For the green class, we can check the most important features for each segment. Here we can see the top features are F5, F7, and F6. And it indicates these features could be considered when creating our separation. So that may give us some idea of how to explain why the green class is different from orange and blue. And then we can explore also the main segments between the blue and orange classes to try to understand how those split. And for the blue and orange classes, we can also look at sort of 2 subgroups in the community with quite different essential features. So here we can see F5 and feature F7 are primary factors. And we can allow the end user to sort of explore this. And again, trying to explain why the model might make these particular classification decisions, looking at these local linear boundaries. All of this can help us get an idea of what might be going on within our complex classification model. And then we can explore the transition between two subgroups. So the curved edge between segment 2 and 9 indicates that there's an angle between the corresponding hyperplanes. So that means instead of a linear segment, now you've shifted. And in the exploration path, the scatter plot in the middle shows the joint area of the two separations where a clear angled transition is depicted. And then that transition path can be animated by the slide bar. We can show this multidimensional projection and explore sort of how this might look in higher dimensional space. And so that's just sort of a demonstration of some of our visual analytics tools here for looking at this idea of locally linear segments. And we had a nice publication on this, the visual analysis of class separations with locally linear segments. You can even take a look at our demo code on GitHub. This was published in IEEE Transactions on Visualization and Computer Graphics. Earn the replicability stamps. Everything you see here you should be able to get from GitHub. And now this idea of looking at these class boundaries in classifier algorithms is really interesting, but there's other research where people have been looking at how can we attack classifiers. And so this has led not to just thinking about, from our team, explanations about these class boundaries, but also how can we explain potential vulnerabilities in these class boundaries. So we started thinking about how can we extend past this work of locally linear classes to what if we have an attacker that's trying to manipulate these class boundaries. And a good example of this is in data poisoning attack. So we have different decision boundaries when the training data set's manipulated, and this can be utilized by attackers to control the predictions from the classifier purposefully. And so we wanted to create a visual analytics system that can help people understand these vulnerabilities. So not only do we need explanations about our classifiers, about why they're making decisions, but we also maybe want to help the model creator understand where their classifier may be vulnerable to attacks. And so we've been trying to think about how we could help people prevent a target instance from being misclassified. And there's two popular attack algorithms we looked at, the binary search attack and the stingray attack. And these are basically data poisoning attacks. And so we wanted to look at some vulnerability measures. So if we have a data instance, so each element perhaps in our training data set is an instance, we can compute how far that is away from a decision boundary, and we can compute what's the minimum cost for a successful attack. And what we mean by a successful attack is, can we shift the decision boundary enough so that this instance I'm attacking gets mislabeled? Instead of being labeled as orange, which is its correct label, can I cause it to be mislabeled as blue? And the reason I might want to do this is I want to use these as sort of ways where I can cause damage to the system. For example, thinking about a self-driving car, can I have the classifier, can I manipulate a decision boundary so it's going to miss stop signs? Can I manipulate a decision boundary so spam will come through? And things like generative adversarial neural networks as well. So we're trying to think about how we can help people explore these classifiers with respect to vulnerabilities. And for this part of the talk, we'll just use the simple example of filtering spam emails. So you've got a training data set of spam and non-spam emails. You use some sort of classifier, and our tool is robust to whatever classifier you want to use. And then on the output, we have a train classifier. And then it goes to the testing stage. You have a bunch of unlabeled emails. We label them now as spam and not spam, and we compare those to the ground truth. Now, what the attacker is trying to do is make specific spams be marked as non-spam emails. We're assuming we have sort of a white box setting where the attacker knows the classification model being used and also has access to the training data. And you may say, well, that's unrealistic, but actually in a lot of practices it's not. When we're collecting training data for spam emails, if I'm a known spammer, what happens is you collect all of my emails and you label them as spam automatically. So now you have sort of a training data set and you have a bunch of email that you know is not spam. If I know you're collecting my emails and labeling them as spam, I can start manipulating content in my email to try to shift this decision boundary. But I have a limited ability to insert data into the training set in a way that's not going to get caught. And so we want to figure out the minimum number of insertions for this goal. So the attacker is trying to change the decision boundary with the minimum number of assertions. And what we want to do is explain to the person using the spam classifier potential vulnerabilities and reveal the attack process and help inspect attack results and explore different attack strategies in order to help people think about defense. So really we're trying to identify these issues to help explain where defense might be necessary. And so we've created a visual analytics system for exploring this. And so again, in a days of poisoning attack, they craft non-spam emails, and these want to be classified as spam. And our analytic tasks are to identify vulnerabilities for specific target instances, provide an overview of the attack result, and diagnose the impact of the attack. So our framework consists of a vulnerability analysis and an attack space analysis. This lets us look at vulnerability measures for training instances, identify weak points, and then diagnose attack results. And so let's look at the vulnerability analysis. Here the core idea is to prevent the target instance from being classified as spam. We've tried to make our system robust to different attack algorithms. So any sort of poisoning attack, here we use binary search attack and stingray attack as our examples, but we feel that our system is robust to other sorts of poisoning attacks. So again, you have your original model. We have a target instance from our data that we want to cause to be misclassified, and we want to think about how adding some poisoning instances, here these 3 new blue dots are poison instances, and we want to think about how those impact the decision boundary. And this new model with these new targets added in is now considered to be a poison model. And we can keep adding more and more instances into our training data set until we get to the attacker's desired poison model. And this then results in the spam emails label being flipped. And again, we have a bunch of vulnerability measures here. We can sort of think about elements that are closer to the decision boundary are more susceptible, because all we sort of are doing is moving the decision boundary. And how much does it cost to attack this element is critical. If you have to insert hundreds and hundreds of poison instances into the training data set, it's more likely that your attack is going to be noticed. And so we try to think about what are the minimum number of poison instances among multiple attacks. And this then also leads to, we can look at the performance metrics of the poison model too. So we know the performance metrics in terms of accuracy, recall, and precision of the original model, and now we can compare to the poison model. If those features haven't changed very much, it may be harder for the end user to detect. It may just look like some tiny shift to them, and they may not notice that now there's a clear point of attack for the attacker. So in this attack space analysis, we start off with just a simple data table view. So for each element in our training data set, so for each spam or non-spam email, we have an ID. And we can see how much it costs to attack that element, how much is going to cost to flip that particular element. So that's the MCSA, minimum cost for a successful attack. And we also know how far that is from its decision boundary distance. We can look at things like accuracy, recall, etc. as well. So we have a whole bunch of different elements that we can then filter and support. A low decision boundary distance means it's easy to flip that element. A high cost attack, though, means it's hard to attack. We want to look at also metric drop. If it has a big metric drop, that also means it's hard to attack. So the data table view is sortable, and it allows us to sort of quickly filter which elements may be vulnerable to different attacks and allow people to sort of explore those in a robust manner. We can also explore by attack algorithm, and then this allows us for a detailed diagnosis on model performance, instances, features, and the local neighborhood. We then use a radar chart for model performance. For this, we considered just showing the poison model versus the original model. The original model's performance is in gray, so we can see things like the F1 score, recall, accuracy, false positives, false negatives, true positives, true negatives, and so forth in the data. And then we can do a comparison of the victim and performance models. We also considered using things like confusion matrix, confusion wheel, but our design rationale was that this radar chart was sort of simple for end users to understand, where the confusion matrix and confusion wheel, while being able to maybe provide more context and details, require a sort of higher overhead for use and learning. We also provide an instance view where we show the distance to the decision boundary for an element, as well as details for each instance, like how vulnerable it is to being shifted. And then we provide a t-SNE projection overview of the data distribution, very similar to our locally linear projection segments. This gives ideas on the decision boundary, classification probabilities, and we also are again focusing on the nearest neighbors to that element, because if that element shifts, it's also possible that some of its nearest neighbors are going to shift across the decision boundary. And we use this sort of glyph for the decision boundary distance, where we're showing the arrow is the victim to the poison class. We're showing how far did that decision boundary shift, and whether or not it shifted across the sort of classification boundary here. We also provide a feature view, so for each instance we show what different elements, what different features of, in this case, the email, make up that attribute of that item, and this can help us see the differences maybe between spam and non-spam, as well as how the different poison instances are being crafted. We can rank the importance of different features in the victim model and the poison model to compare the differences between the two. And we also provide a local impact view, where we're seeing how much the label, the target instance, and the neighboring instances were affected. And similar to what we talked about in the locally linear projection, we can find its k-nearest neighbors, build a KNN graph, and sort of try doing this local representation where we create glyphs of the target instances, the poison instances, and try to demonstrate what's going on in this sort of structure. So let's look at a case study. We take the spam-based email data, binary classification task. We have 57 dimensions. It's a bag of word vectors. Again, for demonstration purposes, we subsample this to about 400 emails, winds up being 243 non-spam emails and 157 spam emails. And here's how our system works. So we're trying to look at the vulnerabilities of a spam filter. So we've loaded our data, and the recall score here is what's really critical for measuring the performance of detecting true spam emails. So we can sort of look at recall, and after ranking the two columns of recall, we find that instance 40 could result in a large reduction of the recall score with the binary search attack. So if they can cause number 40 to be moved across the decision boundary, we can have problems. So we can explore the results of a binary search attack on instance number 40. So we run the attack algorithm, and we can see what happens. So we get false negative become 16 in the victim model, 30 in the poison model, so we're having more false negatives. We can inspect the projection view, and we find that the two classes of points in the poison instances show heavy overlap. So this may cause the possibility of unattacked and unlabeled things being flipped on different instances. Here we can look at our outer ring is a dark red, and there's more than 20 innocent instances in this view whose labels have been flipped from spam to non-spam, and this causes a decreased recall value in the overall model. We can further examine the details of these flipped instances of the instance attribute view, and we notice that most of them are close to the decision boundary in the victim model. So all of this allows us to try to then explore what's going on. We can further look at features and see the variance is quite large in some words such as will and email, and this is showing a large gap between non-spam emails and the instance number 40. So again, allowing us to sort of explore where the vulnerabilities for this instance are and how an attacker might go about sort of trying to attack this particular model. And so this sort of demonstrates the overall views and framework of our vulnerability analysis of our system. And I think this was really powerful in trying to show not only this idea of explainable AI and explainable machine learning, but this idea of explanations of how the classifier works, but now also looking at explanations of where the classifier may be vulnerable to errors and issues. Now, when we start thinking about this idea of vulnerability analysis, I focus a lot on classifiers, but I don't want to give people the impression that that's the only sort of algorithm that's problematic. Our group has also been thinking about graph-based ranking, and we can see this a lot in sort of information manipulation. When you're presented with news stories and Google ranks, all of these are using some sort of graph rank search engine method. Recommendation systems are using the same thing. So if we have people that are trying to manipulate the ranking to promote content, this can be a big problem. We can see this in sort of nation-state actor attacks where people go in and are trying to change how different ranks occur. And so we've been thinking about sort of this sensitivity analysis on ranking algorithms, such as if a node is removed, how sensitive is the ranking to the removal of that node? And this has been pretty common in looking at things like fairness of exposure and rankings to try to understand the sensitivity of this. And so we want to understand how these methods are sensitive to perturbations of graph elements, what specific ranking changes would a certain node removal cause, and what the ranking changes impact cause in real-world applications. So we can create some sort of sensitivity index and the degree of the ranking method's sensitivity to perturbation. And so for any given graph ranking method, we can look at this sensitivity index and try to understand this change in perturbations. And our goal is to be very similar to our other vulnerability analysis, but to help people inspect and understand the graph rankings method's sensitivity. And so to this end, we've created a visual analytics framework for identifying instance level sensitivity, diagnosing perturbation effects, and doing constraint filtering. And so all of this is building on this idea of not just trying to explain the decision results, but help people understand how these results could potentially be vulnerable to manipulations. And this work is going to be presented at the upcoming VAST 2020 conference on auditing the sensitivity of graph-based ranking with visual analytics. And I'm sort of getting to the end of time for this talk, but I think what's really exciting about this is thinking about all the different explainable AI things going on in the Vader lab, from looking at the higher level decision-making process to also thinking about how we can explain decision boundaries. We've been looking at interpretable model training. We've been looking at security as well as reusability of these different models. And so I think this is a really exciting time for this intersection of human, AI, and visualization to think about how we can improve the decision-making process and where visualization fits in, not just in these decision support tools, but also at the lower level for helping machine learning model builders understand and diagnose their algorithms before going out into the wild. So I think this is a really exciting time to be involved in visualization, and I hope people will begin further exploring some methods for this intersection of AI, visualization, and XAI. Thank you.